Hi everyone. Welcome back to another session of the Cambridge MedAI seminar series. It's my great pleasure to introduce our first speaker today, Dimitris Spathis. He's a senior research scientist at Nokia Bell Labs and a visiting researcher at the University of Cambridge, where he completed his PhD. His research enables machine learning to handle complex real-world data efficiently, with a particular interest in health sensing. He has previously worked at Microsoft Research, Telefonica, and Ocado. He will be presenting his work in multimodal, data-efficient, and robust AI for real-world biosignals and the role of generative models. So I just wanted to give a quick note for people that are attending online. Please feel free to unmute yourselves after the talk or to write your questions in the chat. Welcome, Dimitris.
Thank you. Thanks, Ines. First of all, thank you, Ines and the team, for the invitation. It's actually my first time hearing Jeffrey Chia, and I would love to talk to you later about what you're working on as well. So yes, today I will talk about our latest research on multimodal learning. And when I say multimodal, I mean learning from different modalities or different sources, let's say different source of data like wearables, like medical devices, images, sound, all these different sources. We call them modalities in computer science, at least. So the first part of the talk will be about a recent method we developed for time series biosignal data. And the second part, I will discuss some open problems in the broader area. So I want to start from something more fundamental about learning and AI in general. So I had this question: why don't these AI, these statistical models, why don't they learn like humans or animals? And we know that toddlers, for example, excel at these multimodal perception tasks, and they effortlessly learn to recognize faces, understand shapes, and even more in a few weeks, a few months even. On the other hand, AI struggles with these multimodal inputs. And despite advancements in state-of-the-art models, they still struggle with processing and understanding these diverse multimodal inputs. And we see here that in the 5th month or the 6th month, toddler babies, they're able to support themselves and to understand gravity in very complicated situations, right? So there's still something missing in what we're doing. And I think the problem here is that we have all these different sources, and we encounter all these challenges when trying to deal with diverse data streams. So this illustration here showcases a human equipped with an array of sensors and wearables such as smart rings, patches, providing a wealth of information, of course. But the signals we gather, they pose a structural difference. So they have different sampling rates, they have different noise levels and frequencies even. So I believe that to harness this full potential of machine learning and AI in biomedicine in particular, we must overcome these challenges and develop models that are capable of seamlessly integrating all these different signals. I have these two signals on the right side that are particularly important for at least our research, which is the movement signals and heart rate signals, ECG signals. So we know that these signals are structurally different. However, we always treat them in the same way in these machine learning models, right? So going a step back, how do we usually train these models? So we usually ask people, and we create datasets that include paired data of annotations, such as an image of a dog here and the label of this image that it's an actual dog. So these more modern systems require thousands or millions of these pairs, and in order to reach acceptable levels of accuracy. And there's an entire industry of data labeling. There are multi-billion valuations in these companies that they are built on this premise that people will require models that are built on thousands or millions of data points. So human annotators, for example, they're being asked in a crowdsourced way to annotate this image for 5 pence per image, right? But what about signals, like biomedical signals, for example? What if I ask one of you, what is this data point about? You have no idea, right? Because we have no context about this data point. And even if I tell you a bit more about this data point, that it comes from a device that tracks your sleep, and this device is using radio sensors, and Google is actually selling this device. So it's a device that it's like a tablet that can stand on your night bedside table, and it promises to track your sleep stages. And it does this through radio sensors. So even if I tell you this context, you won't be able to tell me if this belongs to REM sleep or a different sleep states. And that's because we have no context about this. So we need a parallel recording of the ground truth. So the recording here of ground truth is probably some EEG signals, some brain signals that the participant, the patient, was wearing while we were sensing their room. So we always need this ground truth in order to annotate this data. And this process, as we have in this proof of concept here, can be 80 times more expensive. So considering that every data point can cost $5 or £4, if we need thousands or millions of these data points to train machine learning systems, we're talking about significant cost. So we're talking about an area in machine learning, like biomedical signals, that we cannot really label data. We don't have access to labels. So we need to find another way. But even if we had labels, even if we had perfect labels, and apart from the higher costs that this entails, we encounter a different challenge, which is noisy algorithms. So even labeled data may be inconsistent sometimes. And while annotation is considered the gold standard, we have annotator disagreement with these labels, with these annotations. And scaling this for real-world settings, especially in tasks like activity recognition. For example, our wearables, our watches, they can track our movement, and they can notify our relatives or emergency services if we fall, for example. So for such a simple task, sometimes annotators completely disagree, right? And that's because these data sets are very noisy. Here we have an example from a published paper from 2019 that 2 different annotators were asked to assess the quality of a PPG signal, of an optical signal that tracks your heart rate on your watch. And they labeled completely different segments of the signal as bad quality or good quality. So we have the problem of labels, and that we have significant costs there. And then we have the problem of annotation disagreement or noise. So a potential solution that has sort of emerged in this area is to do completely without labels, to try to look into the actual data, the actual signals, and pre-train or use unsupervised methods or self-supervised methods to learn from this data. So these data, most of the times, they have a temporal structure. So we can, for example, take a model and ask and challenge the model to predict the future from the past or vice versa. Or if we're talking about an image, predict spectrogram, for example, predict the top from the bottom. So we come up with these tasks, with these fabricated tasks that challenge the model to learn some structure from this data. And this area is called self-supervised learning. And it has been really successful in the past couple of years. So the first models were based on the heuristic, on some heuristic tasks that we take an image or a signal and we rotate it, or we shuffle some parts, some segments of the image, and then we challenge the model to put the things together in the right order. This was in the first couple of years. We're talking about 2018, 2019. And of course, we can create tasks that take into account the physiology. So this is one of our works that we know that your heart rate responds to your activity. So what if you try to put this inside the model, use this inductive bias, as we call it, inside the model. So we take a model that, given your previous activity, your previous movement, it can predict your heart rate. And by doing that, of course, we don't really care about predicting your heart rate because it's not an interesting signal to predict, but the model has captured some very interesting physiological representations, as we call it, some interesting patterns that can predict some meaningful downstream tasks. Let's say your fitness, your VO2 max, maximum oxygen, your energy expenditure, or even some demographics. It can understand differences across populations. So this is, again, an example of self-supervised learning. We have no labels, we have no human annotators, but we challenge the model in a task that has some physiological meaning. So going back to self-supervised learning, we have supervised learning that we always need a label, that the image has a dog label and so on. We have unsupervised learning that most of the times it's about clustering. And then we have this new emerging idea of self-supervised learning that we can create a pretext task, sort of a proxy task. And then we take this model and we apply it to the task that we're interested in, the downstream task, as we call it. And there are many variants of this self-supervised learning. Some popular approaches are contrastive learning that we will talk about later. Generative approaches that are very popular right now, models like ChatGPT, for example, that they generate data, and some other approaches like masking and arrows of time. And all these methods, they try to deal with the input data and hide it in a different way or challenge the model in a different way. But they're all based on this assumption here that we need to create a pretext task. So some approaches right now for biomedical signals, at least, they assume that you have access to positive and negative pairs. This is the contrastive approach I mentioned earlier on the top right. So we have a signal, we transform it, let's say we rotate the signal, and then we take a negative example, a signal that doesn't look like the first signal, and we try to maximize disagreement in the latent space. And we still don't look into labels, so we don't really know what the signals are about. This might be walking, this might be running, this might be arrhythmia, this might be like regular heart rate, and so on. So this is called contrastive learning, as I said, but we still have to pick these negative pairs, which is challenging. So some people apply clustering to create these pairs, but it's still not straightforward. So there's still some computational challenge there. And on top of that, here we're talking about just one modality. So how do we add 2 or 3 or 4 or 5 modalities here? You understand that this becomes very complicated in order to maximize and minimize all these objectives in the latent space. So in layman terms, what we're trying to achieve here is to train a model without labels that on the latent space, it has learned some very good representation of the data. And then we can take this model, for example, here in the bottom, and apply it on downstream tasks that we care about. So some more recent models, these are probably the state-of-the-art models right now. They're called masked autoencoders. They're a bit simpler than the previous approach, so they don't need these negative pairs. We have an input, we have an encoder, we mask part of the input, we only fit the visible parts, and then we ask the decoders to reconstruct the original image. And we can even do so with multimodal inputs. As you see here, we have 3 different views of the same image. This is a very straightforward approach. and it has been very successful, as I said, with models like ChatGPT or GPT models in general. So how do these models work? You have a sentence, and you just hide one word from this sentence, and you challenge the model to predict this word, and they do that in scale with trillions of tokens of data points, as they call it. So this part is the pre-training part, and that's where most models, most companies spend most of their time. Like GPT spends 99.9% of their time training this model with data from the entire internet. So the masking idea is very straightforward and seems to be working. So for biomedical signals, we try to take this one step ahead and apply masking, but not on the input level. We wanted to do that on the latent space level. And why did we want to do that? So we have data, let's say, coming from different sources, audio, sensor, different sorts of biosignals. So we took different encoders, so we have different individual models as inputs. So we have models that are specialized for each modality. And then we take these representations and we just stack them in the same space. And we decided to mask this space here. Because by doing that, we don't make any assumptions about the input space. If you mask data here, you essentially make an assumption that I have to mask sensor 4, that is an ECG sensor. We don't want to make this assumption. We want to let the model make this assumption. So we apply masking on this step, on the latent space, the latent representation, and we can do different, we can follow different approaches here. We can do random masking, completely random, given the modalities and the temporal domain, or even spatial masking and mask out modalities altogether. And then we follow this contrastive approach that you challenge the model, you ask the model to maximize agreement and maximize disagreement between different views. Here we follow the model called VCREG, that is the state of the art right now in computer vision. But I would say the novelty here is this bit and not the actual objective function. So once we do that, of course, we have to apply this model to a downstream task, which is a transfer learning approach here. So what we did is that we found that this spatial masking idea and fine-tuning, like in the downstream task, outperforms other methods. The previous state of the art was this method called COCOA, and of course we have some supervised baselines up there. And so we evaluated the impact of spatial and random masking, and we found that spatial masking works better. And the fine-tuned variant of our method proves to be more accurate as well, which is something expected. So we see that, of course, comparing a pre-trained model to a fine-tuned model might not be a very fair comparison, because always the fine-tuned model will perform better because it has seen the labels, right? So we're trying to understand how robust it is to missing modalities as well. Let's say that you have a medical device is missing because of data loss or data noise. So in this table, we show that, again, fine-tuned models are more robust in inference mode, while the fixed models are particularly robust in the hardest scenario, when there is missing data in both the fine-tuning and the inference setup. And across the board, we also observe that the supervised models are heavily impacted by missing data. And we believe that this is because of our pre-training method. So the supervised models have not been trained with our masking approach. So they're not very robust to missing modalities. Something else we wanted to investigate was the masking strategies and how much should we mask our data. We have seen in other papers in computer vision that the mask on the input space, as I showed before, they apply a very high rate of masking Some of these papers even claim 80% masking of the input data. So essentially, you completely mask out your input data, and that's because of what they claim is that the visual component is very redundant in these data sets. However, in time series, it's not that straightforward. So what we found here is that high latent masking ratios do not result in high performance, unlike the previous works in the input space. And performance drop, of course, is more visible in random masking. So I would say we don't have a clear result here, and we don't know exactly why this happens, but we definitely have differences between the masking ratios. And something else, label efficiency. So once we pre-train, then we further fine-tune with labels. So we have to know how many labels we need for the downstream task. That's the experiment we did here. And we saw that fine-tuning is as good as supervised models. So we can reach supervised performance with fine-tuning, but it's particularly effective in the low data regime, essentially when we have 10 to 20% of labels. And after this point, we see that the performance sort of converges to supervised. But that's very important, at least in my opinion, because even with 10% of labels, we can achieve very good performance. So we don't need all these human annotators to label our data. So some takeaways from this work is that we have evaluated on multimodal signals. I forgot to talk about the actual tasks. These tasks were fall detection and activity recognition, as I said, emotion recognition, and sleep detection. So we try to be as comprehensive as possible and not to focus on a very specific task. And that's very common in machine learning research. And also, we have these experiments on how this model handles missing data that we think is very important, and it's probably one of the strongest advantages of this method. And of course, we don't require any preprocessing of the data or any masking of the actual data, so we don't have any assumptions that other methods have. But of course, the problem is not solved, and that's always because of the data. So self-provision, as I said before, for models like ChatGPT, they use trillions of tokens from the entire internet, right? But in biomedical signals, we don't have access to this data. So of course, we need labels, but we also need large unlabeled data to train these models on. So where can we find this data? At least in the consumer health space, that we talk about heart signals, movement signals, and so on. These datasets are not available publicly. So unlike images or text that you can just scrape the entire internet, here you need to recruit participants and do these longitudinal studies, and then try to understand if this data is meaningful for training these models. So I think the biggest studies out there that they have these modalities are the Apple Heart and Movement study with more than 100,000 participants, and also the UK Biobank study that you might be familiar with. And that also includes these sorts of data that most people don't know about. But 100,000 people from the UK Biobank, they were carrying a smartwatch. And there are some works out there that try to associate this behavioral or objective data, as they call it, or passive data, to clinical outcomes. But as you know, these are not very easily accessible data sets. Probably the UK Biobank is more accessible than the Apple, the private data set of Apple. But going back to my point earlier, we need unlabeled data in this area, and we don't have the data. So all these pre-trained models that are released out there are very limited in size and generalization capabilities. So what can we do about this, right? So we see that the big trend of at least the past 2 years are large language models. So these large language models, they have been trained on mostly text, mostly language, and they show really good generalization capabilities. But what about signals? Can we use them for biosignals, for example? So first we need to take a step back and ask ourselves if these models understand numbers and numerical data altogether. So we have seen in the literature that they do quite well in simple operations like addition or multiplication, division, and so on, but on more complicated tasks, they fail completely. So, the rule of thumb is, of course, larger models in terms of parameters, they do better in these operations. The problem there, another problem is the longer input sequence. So if we have a very long set of numbers, let's say an ECG sensor that samples for 2 or 3 hours, it's not very straightforward how to input this in a context window of an LLM, of a large language model. So there are still some implementation capabilities that we don't have. So we know that these models, these input layers of these models, as we call them, the tokenizers of these models, they're not designed for numbers. So let's say, for example, if we have an input like this, consecutive numbers, we see that the way the model sees these numbers is completely arbitrary. So the model assigns a token to the first number, then we have comma, and then we have 2 different tokens for the next numbers that they consist of 2 different numbers each. So the representation, the mental representation of this input is completely arbitrary. And that's because they're not trained for numbers, they're trained for text. So even for floats, a number like this is represented as like 4 or 3 different IDs. And then we have all sorts of other problems and specific behaviors that are arbitrary. So I think we have a problem there in the first step, the way that these models represent and understand these data sets. So as a small case study, I try to input a very common data set, like let's say you get an Apple Watch and you move your hand and then you try to label this data as walking, running, and so on for fall detection, for example. So if you try to see how models like GPT or ChatGPT understand this data, you see that it's completely arbitrary. So let's say here we have the participant ID, the activity level, a timestamp, and then the 3 axes of rotation, acceleration that we care about. And what the model is actually doing, it's splitting the timestamps into multiple tokens, which is wrong. This should be just one number, right? But the model instead is splitting it into 5 or 6 numbers. And of course, the negative sign, if you look closer, is split from the number, which is completely wrong. And single sensor readings are split in multiple tokens, which is also wrong. So if someone says, okay, can I use models like GPT with my biosignals? The answer is no, right? It's not straightforward. We cannot just throw data to these models and ask and expect to understand this data. So what we need to do here is we need to bridge this modality gap, as we call it, with adapters. So adapters are, think of them as lightweight models that they translate this information into information that can be understandable from a model like GPT, right? That's an animation from Google Research. And there are a few approaches to do that. One is to actually train these models, and there are more approaches on the prompt tuning, on the actual textual input that we give to these models. So that's from a recent paper that came out a few months ago that is sort of trying to follow this approach. So imagine you give a prompt like this to your to a model like ChatGPT, and then you give the actual data. So you expect the model to be able to infer what's going on here. And that's because we give context to the models. We give this prompt here that the model sort of understand that this is AFib and this is a normal signal and so on. And there are a few ways to do that. Of course, we can ask the model to understand questions and answer, which is very straightforward. We can ask the model in zero-shot, as we call it, zero-shot mode, and the model will come up with an answer. Or you can craft more elaborate prompts so that the model has more context. And in the last case, we can even add a layer in front of the model and retrain this layer so that it translates our data to language, which is not language, it's like it's tokens mostly. And as you might expect, the rightmost approach is the most successful as well, because it really adapts the model to the data at hand. Other approaches use pre-processing. So instead of feeding the raw data, we pre-train and we auto-encode our numerical signals, the biosignals, in a representation, and then we add the representation. We don't feed the actual raw data, the raw numbers. And according to this work, this can be beneficial as well. So what I like about these models is that you can take the input space, you can take the input window, and you can concatenate whatever information you have. Let's say you have spirometry data or more clinical values there, and you can merge them with text. And hopefully the model will understand this given the context and given that the data has been pre-processed in a nice way. Last, I think another emerging area here is that the models are becoming more multimodal. And this was a recent paper that came out of Meta of Facebook, that the assumption there is that everything has to run through language because language models are very powerful. So they pre-trained different modalities and they aligned a different modality like audio or video or a movement sensor. They first align it to language, and then by doing this alignment, the model is able to understand different signals. I found the example on the right very impressive, that the model understands that you're cycling only given your watch sensors or your headset sensor. So I think we will start seeing these sort of models even more in the future. But the architecture becomes, it converges to the same sort of approach. So we have a big LLM model, large language model, and then we fine-tune only the bit that we need to fine-tune. The rest of the model is being frozen, as we call it. So the pros and cons of these approaches is that, of course, it's computationally efficient. So we don't really need to retrain a large model with trillions of parameters. And it allows connecting to other high-performing models. So we have a state-of-the-art ECG encoder. We can just plug it to our large language model. And also this makes the system faster in terms of iterations. So we can pre-train this bit, and then we can plug it and further improve it in the future, maybe. Of course, this modularization brings complexity as well. So we don't have an end-to-end system that can be fine-tuned in a nice way because these gradients don't backpropagate all the way back. And as a result of that, the communication between the adapters and the actual language model is not interpretable anymore, because these are just some vectors. They're not human language. So where are we now? So there is some evidence out there that treating these models, these large language models, as generic pre-trained data agnostic models seems to be working. So no, we cannot throw all our data, whatever the source, to these models, but if we're careful, we can come up with some prompts. We can downsample the data so that they fit in their context window, and we also need to curate this data in another way. So if we do this, we might be successful, but it's still early. So we have this. On the other side, of course, we have very elaborate textual prompts. So these are very arbitrary right now. And of course, we have some problems on the tokenizers as well, of how they understand the actual numbers. So this definitely needs more research. So yeah, you can read more on our papers. The left one is the masking idea I showed earlier, and the second one is a position paper on this language model space. And of course, I want to thank my collaborators and colleagues for contributing to these works. And yeah, that's all from me. Thank you.
Next speaker is Katharina Zühlsdorff. She's a graduate entry medicine student and researcher in cognitive computational neuroscience at the University of Cambridge. She completed her PhD at the Department of Psychology here and the Alan Turing Institute in London in September 2022. She researches behavioral and neural circuits underlying reinforcement learning in neuropsychiatric disorders such as substance use abuse and depression.
Hi, everyone. Thank you for joining us here today. Thanks for the introduction. My name is Katharina, and so I'll just move that out of the way there. But yeah, and today I think you'll find, yeah. Right. And today I'll be talking to you about using machine learning methods in order to improve classification and prediction of psychiatric disorders. So as mentioned, I completed my PhD in the Department of Psychology just over a year ago, and I'm now a visiting postdoctoral fellow in the department as well. This is cool. It doesn't seem to be going to the next slide. Here we go. So just a brief summary on what I'll be talking about today. I'll briefly talk about the role of reinforcement learning in psychiatric conditions. I'll provide a brief introduction to the methods that we use, and also touch on the use of graph neural networks to improve prediction as well. So first of all, just a bit of a background. So the main psychological concept that I've been focusing on is cognitive flexibility, which is effectively the ease with which one adapts to changes in the environment. So why is this important? So actually flexibility has been seen to be affected in a variety of psychiatric conditions, including substance use disorder, gambling disorder, and obsessive compulsive disorder, just to mention a few. And it's very important on a day-to-day basis. For example, if we were to travel from the UK to the US, having to adjust to driving on the other side of the road or traffic on the other side of the road, or having to get used to slightly different vocabulary and terminology for certain things. So that would require that cognitive flexible adaptation. And as I mentioned, across tasks that we use to measure flexibility, one of which I'll be introducing shortly, we see impairments across psychiatric conditions. Frequently, these manifest themselves in the form of increased repetitive behaviors. So after there's been a change in the environment, individuals with certain conditions may struggle to adjust to that change. However, we're still we still don't fully understand what happens computationally, so on the neural basis, and how we can really distinguish behavior. So our aim is to be able to better dissociate these disorders, and this will hopefully help us to understand the etiology and better treatment as well. So this is the task that I'll be focusing on mostly, and this is known as a probabilistic reversal learning task, which is very common to study cognitive flexibility. One of the reasons for that is that it is translational, so it can be applied across a variety of species. And essentially the way it works is that a participant is presented with two different stimuli, one of which is the correct and one of which is the incorrect stimulus, but they don't know which one is which in advance, so that's something that has to be learned on a trial by trial and error rather. And after a couple of correct trials, there will be a reversal. So then the other stimulus is the correct one, and the previously correct one is incorrect. And one additional important feature of this is the fact that it's probabilistic. So even if a participant will have chosen correct stimulus, they might get negative reinforcement. So in this case, it would be a sad smiley face. And positive feedback would be a happy smiley face. And so, interestingly, we can use reinforcement learning in order to model behavior on this particular task. So this is something that has been used more and more over the last couple of years. So just briefly introducing reinforcement learning, which is the process by which we can use feedback from the environment, such as a reward or a punishment, in order to adjust behavior. And the idea is in order to maximize rewards and minimize punishments. And so from the task that I just presented, we get information on every single trial. And so what we can do is fit reinforcement learning models to that data. And that helps us understand how individuals track values of the different stimuli throughout the task and how that changes. And so we can extract a number of parameters from these models. Here are just a few, but they're the main ones that we've been focusing on. So there are 3 value-based ones that we've been looking into. Value-based meaning that they rely on kind of whether the previous outcome was rewarded or non-rewarded, so they incorporate feedback essentially, whereas value-free are independent of the outcome. So we have 2 different types of learning rates. Learning rates are effectively how quickly someone will adjust their expectations based on the prediction error. And that can be separated into reward and punishment learning rates. We've also got the reinforcement sensitivity. So how much does the value actually contribute to the actions? Someone with a lower reinforcement sensitivity would tend to explore more rather than exploit the information that they have received. And then we've got the 2 value-free parameters, stimulus and side stickiness. Stickiness refers to the tendency to repeat an action regardless of the outcome. And that can be specific to the side that's previously been chosen, or the stimulus that has been chosen. And just kind of briefly putting that into equations, I'm not going to dwell on this too long, but so the value of each of the stimuli is updated by, or according to the Rescorla-Wagner equation, which is effectively that the value on the next trial equals the value on the current trial, plus the learning rate times the prediction error. So the prediction error being the difference between the reward that was received and the expectation of that particular stimulus of the outcome. So yeah, that was the learning rate that I mentioned earlier. So that highlighted with the red box around it. And again, we can separate that out into reward and punishment. And then we can determine the probability of selecting either stimulus according to the softmax function. And again, we've got the two parameters that were mentioned already, the reinforcement sensitivity and the stimulus or side stickiness. So we have data from now around 300 patients and 130 healthy controls. I'll only be focusing on a subset of these today, and specifically focusing on disorders of compulsivity, specifically substance use disorders, gambling disorder, and obsessive compulsive disorder. And as mentioned earlier, all of these are normally characterized on the reversal learning task by increased repetitive behaviors. So in the first study that I'll be focusing on, we directly compared a group with a cocaine use disorder and a group with gambling disorder, or the diagnosis of gambling disorder, and compared these to healthy controls. And so these are the results, and I will just briefly walk you through this figure because there's quite a lot of information on it. But effectively, we used a hierarchical Bayesian approach, so we don't get p-values as our outputs, but instead we can identify if there are group differences using the highest density intervals, so labeled HDI down there. And effectively, what it tells us is whether there is sufficient evidence for there being a group difference. So the ones in yellow are the ones that will have effectively have had sufficient evidence for there being group differences. And I just highlighted the most important and one other bit to mention is that on the right-hand side of 0 will essentially mean that the healthy controls have a lower value of that parameter compared to the patient group that we're looking at, whereas on the left-hand side, that would be the opposite way around. And I just wanted to highlight the main finding that we had, which was actually that the stimulus stickiness parameter was reduced in individuals with gambling disorder. The reason why this is interesting is because this is quite surprising, because we would have expected stickiness generally to be increased due to increased perseverative and repetitive tendencies commonly observed. However, this was our first indication that this might help us actually distinguish gambling disorder from cocaine use disorder. And in this particular subset of cocaine individuals with cocaine use disorder, we didn't actually have any significant differences, but we know from some other studies that our collaborators that individuals with substance use disorder will tend to have an increase in stimulus and side stickiness. So I'll share that in a moment as well. So kind of the main point being that we can separate out different disorders of compulsivity. Just briefly, what we were also then able to do is link how individuals' expectations change on a trial-by-trial basis and link that to task-based fMRI data. And again, I won't dwell on the details for too long, but the main thing that we found was that activations in areas associated with reinforcement learning and reward learning were altered compared to healthy controls. So there was an altered balance when tracking reward and punishment. And then something similar, well, a slightly different trend, but we also saw a difference in tracking prediction errors in individuals with cocaine use disorders. So again, kind of helping us to distinguish, okay, what's actually going on here in the brain as well. And as I just mentioned, we have had other studies looking at substance use disorder, so not specific to cocaine use disorder, but to a variety of substances. And we also have, in this particular study, a comparison to obsessive compulsive disorder. And again, the main difference here is the difference in stickiness, and obsessive compulsive disorder is also a disorder of compulsivity. So again, what we saw is here that stickiness is actually reduced in individuals with OCD. So taken together with our results from gambling disorder, it can really help us to differentiate these different groups. And we were also able to link that back to what's happening on task-based fMRI data. So looking at particular areas that, again, are also involved in reward learning, but I'm not gonna, in the interest of time, I'm gonna move on to the next topic. So just briefly moving on from reinforcement learning, one other method that we have been interested in are graph neural networks, which are effectively a form of neural networks that use or learn from graph structured data. This data usually comes in the form of having nodes and edges. So in our case, we can also structure the brain as graphs. So the nodes being different brain areas, and the edges being the connectivity between different areas. And so, yeah, we were just wondering whether it would be possible to also predict, in this particular case, ADHD and autism, if we were to structure the graph, brain as a graph from fMRI data. And so there were two publicly accessible data sets, which had just under 1,000 participants per data set. So we had almost 1,000 scans that had both healthy controls and individuals with ADHD. And then just under 800 that had autism, and as well as healthy controls. So what we did was we had up to 80,000 nodes. So there'll be the individual voxels from the fMRI data. And we normalized the signal from each of these voxels, and any voxels with no signals were filtered out. So those time series for each of the voxels were our nodes. And then we calculated Pearson's correlation coefficient between all of the nodes, which were then our edges in our graph. And since in a scan with 60,000 voxels, that would add up to a very, very large amount of different combinations and correlation values, what we did was that we only included edges that had a value higher than 0.9. So in our final graphs, we'd have around 100 edges per node. And so we compared a number of state-of-the-art graph neural networks. So this FFN is actually just a comparison, so it's a simple feed-forward network. Then we had a graph recurrent convolutional network, then a standard graph convolutional network, and a graph attention network, so which incorporates attention mechanisms. And we tested a number of things. So can we just identify or predict autism and ADHD on their own, and are we able to predict sex? So across both data sets, we were able to predict sex with quite high accuracy, and the graph attention network performed the best across all of those tasks. And then ADHD, we were also able to predict with around 74% accuracy. So how does that link back to what I was talking about earlier in relation to reinforcement learning? So the idea would be that this can be further expanded to large-scale data sets, We'd ideally like to be able to predict reinforcement learning parameters with the use of graph neural networks. We want to expand our models to include not only functional MRI data, but also other measures such as functional anisotropy and mean diffusivity. So, for example, diffusion-weighted imaging data. We can include other things like cortical thickness as well, all of which are available from datasets such as the UK Biobank. Edges, so far we're keeping it as connectivity based on fMRI, and then ideally predict cognitive outcomes such as the reinforcement learning measures presented, but of course can also be applied to just disease state on its own. So just a summary, we have shown that reinforcement learning models can be used to clearly separate different psychiatric disorders. And this can be combined with neural imaging as well in order to actually understand what's going on a neural level. Something we're working on is extending on this work to apply it to UK Biobank and also the adolescent brain cognitive development dataset, and then also combining this with graph neural networks for further classification and predicting disease. Some of the collaborators that I've been working on this with, and yeah, thank you very much for listening.